Hello everyone, welcome back. So let us continue our discussion on torsion. We are in week 10 and this is our second lecture. Now, as we planned earlier that today we are going to discuss non-uniform section and how the torsional expressions are for this type of sections that we are going to derive today. Actually, this kind of variation in cross section of a shaft often we see in case of mechanical devices, and that's the reason. Let us see how we can solve this problem. But before that, if you recall, the expression we derived for a circular shaft is phi is equal to T times L divided by G times IP. Right? Now, non-uniform bars non-uniform cross sections, it can be of different type, as you can see one example on your screen here. Now, in this example, say we have a torsion T1 is applied here, then T2 is applied here, then we can apply a torsion say here T3, and this end we can apply another say T4. Now, over the length, we have a variation in cross section as you can see here. And then over the length, we have different segments with different value of torque applied, right? So what effectively we can do, we can split this into different segments. So ith segment having a torsion say Ti, and for that we can find out what is the phi. So for individual segment we can find out phi, and then we can sum it up to find out total rotation. So for total rotation we have I equal to 1 to say n if we have n such segments, and for each segment we can find out what is phi I from this expression, and then we can find out the total rotation of the shaft, right? So it will be I equal to 1 to n Ti Li divided by G. Actually we can have Gi, different material in different segments, times I Pi. And that gives us the total amount of rotation we have. Now, the moment we have total rotation from the individual rotation phi I, we can then find out for individual rotation what is theta, that is phi I divided by Li, right? And then we can also write down tau I is equal to Gi times Ri times theta. So that is the effective value of stress and its distribution within the ith segment, right? So we can solve this problem. The reason is we have uniform cross sections over a particular segment, and we divide the complete length into different segments, and for each segment we can solve the problem and we can complete the exercise. We are going to take some examples. The moment we'll put some numbers, it will be further clear. But for the time being, it is not very difficult, simply because over a particular segment, for example, if you consider this segment, over this, it is effectively a shaft with uniform cross section. So we can easily adapt the mathematical model that we have developed. Now let us move to a different non-uniformity, as you can see on your screen. And in this case, as we progress along the length of the beam, the cross section changes. So along the longitudinal direction, if we apply torque, say T, then the question is for this segment, how we can quantify the amount of rotation. For that, what we do, we consider small segment at a distance x from one end, and let this be dx. So for this segment, let the amount of torsion be dx. Then the rotation d of phi is equal to dx times the length, which is dx, divided by material g times I dx. Now if we integrate both sides, then effectively what we get? We get total rotation over the complete length, say capital L, and that is 0 to t dx dx divided by g times x. If tx is constant throughout, obviously this will be replaced by a constant. Effectively, we have to evaluate the polar moment of inertia in that case for the small ring you can see here, and then we have to integrate over the complete length, which is capital L here. Now that solves the complete problem for this non-uniform section. So let us take an example. So in this example, we have non-uniform shaft, and we apply again a torque T, and then this section we have diameter D1, and this section we have diameter D2. So what we do, we again consider a segment. Here you can see at a distance x from the left end. We can consider from either end, it's not a problem. And the length of this small ring is dx. Now the diameter d at x, it's not dx, what you can see here. So d at x is equal to, we can evaluate d1 plus d2 minus d1, that is the change in length, change in diameter over a length of capital L times x. And IP of x is equal to pi dx to the power 4 divided by 32. Now in place of dx, we can write down the expression. So this is pi by 32, and then we have d1 plus d2 minus d1 divided by L times x whole to the power 4. Now for this small segment dx, we can now find out d phi, which is equal to T, that is the torque applied over a length dx divided by g times I dx. And now if we integrate over the full length, so 0 to L, and on the left hand side we have 0 to say phi, then total rotation phi we can evaluate. This you can write down, say a dx divided by b plus cx whole to the power 4, and here a is equal to 32 t divided by pi g, then b we have d1, and then c we have d2 minus d1 divided by L. So we can perform this integral and you'll get a by 3c times 1 divided by B plus Cx whole cube. So effectively we get A by 3C within bracket 1 by B cube minus 1 by B plus Cl whole cube. And if you put the expression of ABC here, you get 32 T times L divided by 3 pi G D2 minus D1 times 1 by D1 cube minus 1 by. So that is the expression. I leave this as a exercise for you, just cross verify. So we get the total rotation over the two ends, and the expression you can see here. And for the linear variation, now we have the total rotation over the shaft, right? So you can see how we can use the theory that we have developed for torsion for this non-uniform cross section, and we can find out the total rotation, right? Just do this problem at your end. If you have any difficulty, do let us know. Okay, so now let us take a different example. So in this example, we have a fixed end. Then at 2 points, say here and there, over the longitudinal axis of this shaft, we apply torque. Say this is T1 and the second one is T2. Let us mark the points. So this is A, this is B, C, and this is D. Now there is no torque applied at the free end, so this free end is allowed to turn freely. Right. Now the value of T1 is 2250 Newton meter. T2 is equal to 1500 Newton meter. Diameter D is equal to 0.075 meter, and the G is 80,000 megapascal. Our task is to find out the value of phi. Note, one end is fixed, the other end is free, and over the length we apply two different values of torque, T1 and T2. Now, if you note the segment AB, over that the value of torque TAB is equal to T1 plus T2, right? Now that means this is 3750 Newton. What about the next segment, T of BC? Over this we apply actually T2, and that is 1500 Newton meter. And TCD, because this end is allowed to rotate freely, the amount of torque over this section is 0. Now we can calculate the amount of stress in the section AB. So tau AB is equal to, if you recall the expression, 16 TAB divided by pi times d cube. It is a circular cross section, so the maximum stress will develop at the edge And for that we have this expression. So what we get, 16 times 3750 divided by pi times 0.075 whole cube. And the value of this expression is 45.27 into 10 to the power 6, that is in Pascal, so 45.27 MPa. Similarly, we can also find out tau BC. For that we have 16 times the value of torque, and that is 1500 divided by pi times, again we have uniform diameter, so 0.75 whole cube, and the value of this tau over the range BC is 18.11 into 10 to the power 6 again, so we can write it 18.11 megapascal. Now for the circular cross section, we can find the value of IP. IP is pi d to the power 4 divided by 32. And if we evaluate this expression for this diameter of 0.075, it is 3.1063 into 10 to the power minus 6 meter to the power 4. So we have all the information. So what we have to do, we have to find out phi for each segment, and then that will give us total phi. So we have T1 or TI LI divided by GI and IPI. So what we have is, for the first segment, 3750 times the length. So the total length is 1.75 meter. So we have here 0.5 meter, 0.75 meter and 0.5 meter. So Li for the first segment is 0.5. Then we have 80 into 10 to the power 9 if we express in Pascal times 3.1063 into 10 to the power minus 6, plus for the next segment we have 1500 times 0.75 divided by, again, the same value of G and IP. So if you evaluate this, that I just leave it as an home task, this numerical exercise, you will effectively get 0.0121 radian. Just check this at your end. One point to be noted here, the third segment CD has no torque, so we do not consider that because the torque is 0 there, right? So that's the reason we write the expression for the first segment AB and the second one BC. So from this example, you can see how we can evaluate the stresses over different segments of the circular shaft, and we can also find out the total rotation, which is a summation of the rotation from the individual section. Okay, so let us continue our discussion on the torsion of a circular shaft, and if you just note the deformed shape for this uniform cross section, we have torque T applied at the end, And because of this torque, as there is no other force, we have this small segment ABCD, and over this small segment, if we identify the stresses, we have only shear stresses acting. This is the value of the shear stress. That means if we draw the free body diagram of ABCD, what we have is a case of pure shear, right? Now for this pure shear case, again we can consider a plane which is at an angle, say theta, and for that again we can find out the normal and shear stress. This exercise we have done. Let us just quickly do it in case of a segment which is having pure shear, right? So this angle is theta and this is say sigma n, and we have tau n. For that again, if you recall what we do, we draw the free body diagram of this segment, and then we apply equilibrium, right? Let us quickly solve this problem. So if we write down the forces, recall this angle is theta and this area is A naught, right? Then the force here tau times A naught, and here it is tau times A naught tan theta. This force is tau n times A naught sec theta, and the normal force is sigma n times A naught sec theta. So if we apply equilibrium along n, what we get? Sigma n A0 sec theta is equal to tau A naught sin theta plus tau A naught tan theta times cos theta. So which gives sigma n is equal to twice tau sin theta cos theta. That means this is equal to tau times sine of theta. Similarly, if we consider all forces along this direction, say n prime is equal to 0, then what we get? We have tau n A0 sec theta is equal to tau A naught cos of theta minus tau A naught tan theta times sin theta. So therefore tau n is equal to tau times cos square theta minus sin square theta, which is tau cos of 2 theta. Now from these two expressions we can find out the maximum value sigma n max is equal to plus minus tau, right? That you can identify from this expression. Between 0 to 360 we have this variation, and similarly also we can find out tau n max is equal to minus plus tau. Right? Okay. Now, if we consider again the same element and the deformed shape you can see here. So we have A, B, C, D, or let me write C, D. Then after deformation, we have A prime, B prime, C prime, D prime, and the reference axis you can see here. Due to the shear stress tau. So at 45 degree, if you just note this maximum value of sigma n, what effectively we get is on this direction, we have sigma n, which is tau, and in the orthogonal direction, if you look at the value of sigma n, which is minus tau, right? So that means it is acting this way. So tau, and here one is tension, another is compression. And if you look at this diagonal, one diagonal is extended and another diagonal, if you look at, it is contracted. Now this point, if you say E, then we can quantify this elongation along the diagonal, right? So the elongation of the diagonal, say BD, is equal to, at the beginning, if this edge is H and H, so we have root 2H. So the increment over this length is the original length, which is root 2 times H times epsilon, and epsilon we can quantify, which is 1 by E times tau, that is the sigma here, plus, because we have a negative tau, nu times tau, right? That means LBD, that is the total length, we can now quantify, it is root 2H, within bracket, we have 1 plus tau by E times 1 plus nu. Right? Okay. Now, if you look at the angle ADE, this is cos of pi by 4 minus gamma by 2, right? So this angle is cos of, sorry, this angle is pi by 4 minus gamma by 2. Total angle is pi by 2 minus gamma, and that's how half of that we get here, right? Okay. So now this angle, cosine of this angle is equal to length BD divided by twice H. Okay, so if we expand this cosine of pi by 4 minus gamma by 2, so what we get, cosine of pi by 4 times cosine of gamma by 2 plus sine of pi by 4 minus times sine of gamma by 2. This is equal to, we can put the expression of LBD from this equation we have already derived, and then what we'll get is 1 by square root of 2 plus we have delta BD divided by twice h. Now if you have a small rotation, then cos pi by 4 is 1 by root 2, and for small rotation cosine of that value is 1 plus sine of pi by 4 is 1 by root 2. Then for small rotation sine of gamma by 2 is gamma by 2. Then we have 1 by root 2 plus we have delta BD divided by twice h. So effectively what we get, delta BD is equal to h gamma by root 2. Now in place of gamma, we can write twice of epsilon, and which is equal to tau by E times 1 plus nu. So effectively what we get epsilon now you can see we can express total strain is equal to gamma by 2, which is equal to 1 by E or tau by E times 1 plus nu. So what we have, tau by twice G is equal to 1 by E times tau times 1 plus nu, right? So we have G is equal to E by 2 into 1 plus nu. This expression again we derived earlier when we correlated stress and strain at the very beginning. Today for the circular shaft also again we derived the same expression, and what we get today is the expression here, the expression of phi, which gives us the value of G from the experiment, right? That we can again cross verify for the same material. We can cross verify with Young's modulus, right? Okay. So that concludes here. As we progress in the next lecture, we will see how we can further solve different examples of this circular shaft. Very often these circular shafts are used to transmit power. Now, normally a mechanical system having a shaft, that shaft rotates with some RPM, and we will quantify the power transmitted by the shaft, and for that shaft if there is a torque developed and how much rotation it experiences at the ends, that also we will quantify. We will take some example, and with that we will see how the power is transmitted through circular shafts. Let us stop here. We will continue in next lecture. Thank you very much.